Thank you for joining our conversation today. I named my presentation "The Future I See" from my own point of view. I would like to share some background about the fact that we are all cyborgs already. I want to point out at the intelligence in solid state that we started like less than a century ago to expand our intelligence to electronics, and then to personal computers, and then supercomputers and cell phones nowadays. They're part of us. Like we look at our phones like less than like 10 to 20 times a day, and we're constantly integrating our lives with computers. And the internet in this spectrum is I call it an organizing soft network. It's networking the information and people, which is a software based on the solid state platform, which is computers. So nowadays we have already integrated music, videos, and more or less touch. I point at these three senses because these are the most integrated information that we are nowadays communicating through solid state intelligence. We used to massage each other as humans. Nowadays we can do it thanks to solid state and materials, non-living materials, which are programmed using solid state electronics. We have integrated music and videos, and actually a couple of decades ago we already expanded our cutting-edge cyborg technologies into a spaceman, which we advanced living in an environment that was almost impossible to exist for a couple of seconds. So it's no surprise if we would go back to the sentence that we are already cyborgs. But these two senses, I would like to mention, not to forget, that they are not already integrated with solid state intelligence. We have not recorded any taste into digital, as long as I know, and smell is pretty problematic at this point because it's very sophisticated. One day we would totally enjoy having an electronic nose or tongue and recording them and sharing them with each other. So on one hand we have the intelligence in solid state, and on the other hand we have it in our biological bodies. So how do we interface them? We used to interface them with vision, with our ears, sound waves from the air, and touch, of course, with just touching materials. But there are many more interfaces that we have not yet developed or explored. So I would like to categorize two types of hardware interfaces. The first one is using neuroplasticity, of course, as well as recovering technologies, but in general, neuroplasticity means that human brain can adapt to the new sensory information. So you can basically, in theory, in principle, introduce new sensory domains to human brain. You can introduce infrared, you can introduce UV as new spectrum of vision, or any type of information you can imagine. So on one hand, there is the ideology of transhumanism, which is the logo, but that introduces totally new sensory domains. It changes the human experience as it is experienced before. On the other hand, there's like the more traditional, or I would say conservative, way of looking at technology, and hardware interfaces, which is medicine. That somebody just loses the normal eye, we just replace it with an electronic eye, or a nose, or an ear, or any other organs, heart transplants, kidney. So for a long time I thought about the hardware interfaces, and are they really going to go extinct, or they're gonna be there for us? So I would say at this point that hardware interfaces, they are very, very difficult and cumbersome, and they have a lot of issues at the moment, but I believe it's inevitable. I don't think there is going to be any better alternative to gap the bridge between solid state and biology in order to integrate these two domains of information. So if I just name a couple of problems of hardware interfaces, one of them is aging. Your phone dies in 2 years, doesn't it? So you just change it, you buy a new version. But what if we transplant an electronic implant into a human body and then it just ages and dies? I don't think anybody would like to have a surgery, open surgery every year or every 2 years. So that's a big problem. The other one is selectivity. Most of the time we would like in the future to stimulate or record individual neurons, for example, but nowadays the probes, the optical probes or electrical probes that we have, they are targeting many neurons at one place. So our selectivity is very, very, very poor at the moment. The other thing is power delivery. You know, the batteries are one way that we charge our cell phones, our cars, our laptops, but they are so big for human implants. So they're not very efficient most of the time. In research environments, we use wireless power transfer, which is also cumbersome and not very, very practical for commercialization. So power delivery, there's another technology that harvests energy from human body, from your veins, from your blood sugar, from oxidation in your blood with some solid state materials, and so on and so forth. So power delivery is another huge path of research in the next decade. Biocompatibility is another problem. So we have a lot of solid state materials that are harmful to our bodies. They can be amazing, they can have many features, but they just can't be exposed to body. So that's another problem there. And it's good to mention that nanotechnology by itself is not very biocompatible. So most of the time people get so excited about nanotechnology. It's so small, you can do so many things and just attack every cell you have in your body, but at the same time it can be very hazardous because you cannot control the interaction of nanoparticles with your biological cells. So that's another problem, an aspect of hardware interfaces. And for size and accessibility, which has been pretty done a great job in the past decade using like micro technologies, but it still is a problem. So I would like to categorize two major brain interface technologies for you that you may have already seen some of the examples in the technology market. So it's invasive and non-invasive. Invasive means that you are basically having a surgery, you have an implant under your bone, under your skull, and there is an invasive injection of an electrode or optrode. So that's usually for permanent solutions, but it has a lot of issues and problems until it can get a commercialized technology. Non-invasive, as you may have seen already, there are a lot of technologies out there using electrical recordings of the skin. It's one of the most practical that we have already seen, and it's pretty working in some biofeedback technologies. It can help you meditate better, switch between your alpha, beta, and different waveforms of your brain. So it's a biofeedback from your brain, which can be pretty helpful. So what I do now, as my own research, which is a small, very negligible small contribution to the whole exponential technologies, is that I try to stick to the idea of extending human sense, and then I just, based on the constraints of my environment and the city I live, the university I study in, I picked up this project, which is not very novel, or the idea has been there for a couple of years. It's intraocular pressure sensor, IOP sensor. You probably have heard of it. Glaucoma is a disease that more than 40 million of people already are facing it in the world, at least, and it means that the pressure in your eyeball increases. We don't want that, because eyeball is like a balloon, and then after a certain amount of pressure, the pressure can go and damage your nerve cells, and there's no pain, so we don't feel anything unless it's too late. As you see in these pictures, this is the normal vision, and early glaucoma, you start to lose the edges, and then by the time that you get here, it's too late. There is no cure. There are medicines that they can slow down the process and take the pressure of your eyeball in balance, but there is a problem of monitoring the pressure of eyeball. We don't understand when we have to take how much medicine. There are traditional ways. This is like one of the most portable, available commercially product that uses some mechanical touch. As you see, there is a needle touching the eyeball, and it's based on the strain and stress and the reflection of the impact to the needle. It mechanically records the pressure, but it's very inaccurate and unreliable. So the technology, electronic technology, is coming to help, and it somehow more precisely and more accurately it records the pressure, and wirelessly, like after you implant this lens into your eye, you can wirelessly record and read and monitor the pressure in your eye. You can do that many times a day, and based on the numbers you read on your device, you can take proper medicine. So I call it a biofeedback used for medicine. You're getting a feedback, you're reading, you're monitoring a signal in your body that normally our brain is not evolved yet to do that for you. Nowadays, if you hit your leg to a hard object, it hurts, and then you understand something's going wrong. So, but our body has not evolved enough yet for many diseases. So that's what our brain intelligently doing, manipulating the environment in solid state in order to make tools to evolve. So that's about solid states. There is another whole chapter of technology that I'm very enthusiastic about. It's biofabrication, it's synthetic biology. Nowadays we all hear of genetically modified organisms, and most of us are not familiar with what's going on, and we are scared of it. But at the same time, there is a huge futuristic potential in synthetic biology, and printing a human organ is just one small example of it. So Drew Envy in Stanford with Adam Arkin, they are the pioneers of this biofab, which is an open source platform to to make classes of different genetic products. They're basically making logo parts of DNA that they can put these logo parts next to each other and make who knows what organisms in the future. So one day you can have a seed and then plant it on the ground, and when it grows like a tree, it gives you some electronic chips, and then or computers or whatever, probably living computers or intelligence. So pretty much the line between non-living and living are getting manipulated, and I am not contributing or affiliated with any biofabrication or synthetic biology, but I am constantly monitoring the advancement of their research. So yeah, that's about it. Thank you. And I have a Facebook page that I share what I find interesting. I call it Biomachinist. So I would appreciate if you like it and just stay tuned. It helps us get connected. So thank you for watching, and I'm excited to hear your comments.
Number one, you were mentioning wireless power delivery to these mechanisms, and you were saying that there are problems associated with that. Can you maybe briefly what that might be the solution to the issue of getting power to these very, very small devices? If considering that you can have a large device just outside, and you can be in extremely close proximity to the devices, so it seems like the full principles are favorable to wireless power.
Yeah, one of the biggest problems is when you have a wireless communication, you're using antenna, and even if for power, you have to have an antenna that works in a certain frequency range. So the higher the frequency that you're working with, the smaller your antennas can be. At the same time, you cannot exceed a certain amount of frequency working nearby biological body, like human body, human tissue. So it's biohazardous to exceed a certain amount of frequency, which means you cannot get your antennas smaller than a certain amount, certain size, which is by itself a problem, because you want to have smaller and smaller devices, but your antennas can't get smaller after a certain point. So power delivery. So
high frequency.
Yes.
Sorry. So high frequency electromagnetic waves are not safe for biological creatures.
No.
Even though it's non-ionizing radiation, though, isn't it?
It just warms up the tissue. The temperature in the
it warms it up. Okay, it's not okay.
And and also I would like to give you some numbers. Like 1 gigahertz is basically like the each of the standard. Like you can usually go above 1 or 2 gigahertz, which is Bluetooth is 2.4. So that's why Bluetooth in high powers is by itself not very, very safe. Yeah.
Okay, can I just ask one more question? So you mentioned the problems of getting close to neurons, and I remember I mentioned last week that article about putting devices into stents in the veins.
I think I'm going to go to the
Is that an idea?
Yes, it's stentrode. They call it stentrode. Like there's optrode, which is optical probe, electrode, which is electrical probe, and there's this stent technology.
I'm getting bad signal. I need to go.
But if I would like to hi.
Hey, hi. Hey, sorry about that. I think I'm like mumbling.
No problem. Welcome, Zach. We had a question about stentrode, like some probes that they just inserted through the human veins, and they can just stick to the walls of the vein and start recording signals. But one of the first things that came to my mind when I read about this technology is that it is not accessing the neurons directly, first of all. This is recording signals from the vein environment. This is from the cells, from the walls of the vein, and from the particles that are swimming inside the blood. So these are called like indirect signal recording. They're never like targeting because we cannot put those stents into the very, very naive and small veins inside the human brain. As the furthest they can go is like until your neck, and that's about it.
Oh, I think the idea was that they would go right in the brain, that they would go past the blood-brain barrier and like and then right up next to neurons. But I see your point though; they're still not touching directly the neurons, so they're still not issues.
Sure, they're not developed. The idea is theoretically possible, but with the current technologies that I can imagine, that the stents that you can make right now, they cannot go that small yet. And
oh yeah, that's a good point. Yeah, that's true. Okay, currently.
So I'm sort of jumping in the middle of this, but interestingly enough, I met some folks who were just at my property earlier today, who are working on ion-gated voltage channels with neurons and cryogenics. So I don't know how it is that their work relates to this topic, but I plan on meeting with them.
Yes, I would ask.
I know that they are doing a lot of work in photonics, particularly, and this sort of thing with neurons and.
Yes, ion channels and gate-activated transistors. Is that what you're mentioning? Hello, Zach? Okay, I guess we lost Zach. So until he comes back,
I'm back, I think.
Okay. Okay. So would you like to elaborate more on your comment?
Yeah. What part did you guys like? I feel like it cut out there.
Could you repeat again, please?
Yeah, certainly. So I'd met two folks who had come by my place visiting another startup that's doing photonics computing in our garage, and they are doing. I talked to them briefly, and they're doing something with cryogenics and voltage, ion channels in neurons. So I'm not sure exactly what the full nature of their work is. I plan on hopefully connecting with them more later on it, potentially.
Okay, could you explain cryogenics? Is this like just low temperature technologies, or?
Yeah, I wasn't able to get into a very long conversation. We were only talking for about 10 minutes or so. So I'm gonna find out more.
Okay, that's a very good indication. Or probably you're talking about some neural interfaces.
Yes.
And it's a new technology, cryogenics.
Yes.
I definitely just right away after the conversation look it up, and we can share more about it. Anybody comment on cryogenics?
Yeah, I'm sorry, Haas. I don't think I'd be in favor of freezing my brain just to communicate with other people. I would not be the first person to volunteer for that experiment. I'm sorry.
Yeah,
okay.
Sure. Actually, and this is what I shared with them, is that my take on this issue around brain interfacing is quite a bit different than this the approach of going into the brain with neural nanocytes and interfacing with it at the neuronal level. And now you'll have to bear with me. It's kind of a different take on this, but and it's pulling in from some places that aren't looked at too closely, and really has a lot to do with understandings with biophotonics, and so there's a little bit of work there to be done. But basically, our cells communicate through the medium of photonics. They send out signals in the terahertz frequency, the far infrared at about 10,000 nanometers is the wavelength, and it's used as a way of signaling inter and intracellularly. And my strong hypothesis, and I could go into the provenance of why I'm thinking this way in a more like one-on-one type session, is that that it might be very tenable to use these techniques of sensing changes in the electromagnetic field of the individual, that is the photonic field in the far infrared range, and to be able to discern very precisely changes in this field, and then communicating those changes and affecting change itself is another topic but first it's being able to measure this field in a reliable way, and we have the physics behind this to do this kind of stuff today. So and then how to interface between is another challenge. One thing to note that is really challenging with brain-to-brain interfacing is that each brain encodes information and experiences in a completely different, well, not completely, but in a different way from everyone else. Like my encoding of certain symbols or these words themselves are different than in every other brain. So there's a challenge there of translating experience from one brain to another. But I think it's totally possible with advancements in machine learning techniques and so on to be able to do this mapping process. But it's going to be computationally expensive, is my feeling.
Okay, I have a question. As long as the physics is concerned, I am totally with you. Like, there is no doubt that it is possible. Like, it is plausible theoretically. But I'm very curious about the technology, about the tools that can be used for manipulating electromagnetic waves in that scale and selectivity that we need.
Yeah. Okay. So there's two interesting pieces here on the physics side. One is there's a paper that I have from 2012, and I think there's a few other papers that I found too, but talking about using radar actually to detect changes in the electromagnetic field orders of magnitude greater than other techniques, and so that's you're going to need like a really good way of detecting these changes, because they can be very small, so you need very precise measurements, and then if you're out in the wild, you're going to have to be able to filter it from all the other noise, which is a different challenge. But in a lab setting, in a room, this should be generally approachable with the right group and the right tools with today's technology. Now, with the interfacing with it, or the modulating of this field, how one would do this, well, first of all, one would have to be very responsible and ethically constrained, because it could be bad otherwise. So I think I'll just like leave it at that for right now, and maybe later talk about some ideas I have on how one would modulate it. But I do have some ideas.
Yeah, so you're saying that there's sensors and emitters in neurons for a particular wavelength of light, or
it's actually fundamental to every cell. Like every biologically alive thing emits light in about the same bandwidth.
But it also has sensors for that light?
Yeah, it's part of the cell. Like even in plants and basically everything that we proclaim to be biologically alive, it has this process. Everything that has a cell, each cell is able to uses this photonic field as more or less an organizing medium to signal inside of itself, across the cell inside, as well as radiating to other cells. So basically, it's using photonics as a signaling channel to its environment. And
do you have any links to anything that talks about it?
Yeah. It's actually pretty sparse in the literature on this. I do have a couple of publications that have been collected and edited for biophotonics, which talks about this. So maybe if like we can have like a follow-up thing after this where we say send links to XYZ. I can follow up with that. It's going to take me a minute to dredge through all of my resources. Like I have a lot of various things.
Cool. Yeah, that sounds really cool. So,
are you on the Zachary? Are you on the Facebook message group there?
Yes, I am.
The link you like?
Yep. Yeah.
Yeah, just throw up a link because I'm googling it. I'm not finding what I want to see, I guess. So yeah, feel free. Sounds interesting.
Yeah, I know. Like I said,
go.
The research on this is sparse, which is really surprising because it seems to be
no, that's fine. We'll just check out
really fundamental. So yeah.
Yeah, for sure. We'll just check out your link. Sorry, just conscious of time. We have just a few minutes left. So yeah, Will, I think you're asking a question. Go ahead.
Oh no, that was it.
Yeah, I have a question, if I can ask. Hello?
You are authorized.
Okay, no, because because you know if you can hear me, because my microphone is going on and off. Yeah, my question is on, okay, by the way, Zach, this is very interesting. If you can send some links, that would be great. And I was already looking at it, and I was thinking that maybe the signal comes from the DNA, but I don't know. This is very interesting, so I'll go through this. My question is more like related to Mohammed's presentation, and also it's a follow-up from Michael's questions about the powering of this device. So if you have a device that is connected to our body, of course the power is going to be an issue. So my question is it possible? And I guess yes, it is, but you know, it's just more like a provocative way. Is it possible to have a self-powered device? So meaning that we can use the so-called piezoelectric harvesting material that you can push with your body, and you can create electricity that can drive the device. On the other hand, also we have a thermoelectric device where we can harness it to produce electricity, and our body is full, so we can use that heat to power a measurement device or a human robot interface. So those are the two questions. Also, we can also combine the two energy sources actually. and to produce even more power. And not even to mention the energy coming from biothings, for example from ATP, that is a product coming from the cell. You can measure is actually the source of life. We can get that energy. So I'm thinking that our body can be also a source of energy that we can harness to power interfaces and devices. So this is like more a question or a comment. Yeah.
So it sounds like what you're saying is that you know, little micro machines, little mini machines that are kind of self-contained. They have the energy that they gain from the environment that they're in, which is your body, and that powers them, and then they do their thing. Is that what you're thinking?
Yeah, exactly. In fact, there are already few devices like pacemakers that are investigated to be powered by piezoelectric devices, and so in that case you wanted a battery. For now, research is very on stage, but in the future there may be a big deal. So, and I was thinking of extending this to thermoelectric devices. Yeah, so maybe just a comment and just to go there some ideas that I'm sure they've been already investigated, but
Yeah, I like this part there, Romano.
Yeah, exactly. As you can see, like in biology, we can always harness power, and these are actual projects that have happened, like using like animals and human organs. But one important comment I think for now is that at the moment, the power that we can harness from bio tissues or blood or whatever, it is not even close to what we need. So there's a huge gap between the power that we need to charge to power our devices and the power that we can harness. So it's just a matter of technology, but in principle, it is totally possible and proof that it's working.
Oh, okay. Right. Perfect.
Mm-hmm. So I've been thinking lately about like how you could like interrupt just your spinal cord, and so like to make your body disassociate and then integrate just with your brain stem, because a lot of your other senses, like you talked about smell and what was the other one? It was smell and taste, right? So those two are up in your head as well, but the eyes definitely. With VR, like with virtual reality, you get a deep tie into your subconscious. You're kind of you're cutting off the real world and introducing, high quality light patterns into your brain, and then auditory is pretty straightforward. I think you've had that for a long time. With good high quality earbuds. Which block out the real world and replace it with high quality sound waves. Maybe there's some better stuff with like piezoelectric arrays that create the shape of the sound as opposed to just the 3D shape of the sound as opposed to just the waveform. And then there's so that's sight. Then you have hearing and. So for smell, like you said, that's really problematic. But I have a friend that made a device that you put on your nose, and it will release. You can put in little vials of different things that smell, and it'll release them I don't know if it uses like an inkjet printer cartridges or something. Anyway, like you said, that's pretty hard. Then if you to do your tongue, it's kind of weird, because you go in and it's weird to put something on your tongue. That just is really, I don't even know how that would work. But then also you have your body, so your feeling. So like if you wear they have those those suits. You put on the whole suit, and it simulates some patterns along the skin. But you know, but they're kind of like, you know, they don't. You see your whole body to cover your face or everything. You know, it's not. It's only usually like sections of your body. But that kind of goes into what you're saying about you know, plasticity, where those guys that did the thing on the back. So there's a lot of sensors on the back that you don't generally include in your neural day-to-day processing, but yet there's a lot of neurons actually connected to them, and if you stimulate those and move those, that they can, you know, be retrained to do a lot of things. Like you can learn how to you know, learn how to hear, like deaf people can learn how to hear with the patterns on the back and stuff like that. You know, so I was thinking that, you know, if there was some way to interrupt, like you're not that far away from your spinal cord, so if there's some way to non-invasively just interrupt, most of the EEG stuff we have focuses on the, you know, cerebral cortex and our upper brains, but I was thinking if you could like somehow interrupt the flow of signals down into the rest of your body, you kind of paralyze yourself, and then, you know, non-invasively though, and then you could turn it off and on, like an off-on paralyzation, and then you could, and then maybe it's a little bit closer to the skin or something, where you could do something in there where you'd have control of that, and that way you could have all these other systems. That's something you could do right away, maybe. I don't know. I was just thinking about that last couple of days. So anyway, that's all.
Fantastic comment. Thank you.
Interesting.
So, is there any other specific question for now?
None for me. Thanks.
Not for me either. Thanks.
Okay, so thank you all for your participation in the third presentation of Let's Make the Future group. And I would like to have Zach personally present next week, but we can manage that for either wheel. So thank you again, and have a nice week. Thank you.
Yeah, see you guys next week. Thank you so much, Will.
Thank you.
Awesome.
See you next week. Bye-bye.
This was a lot of fun. I look forward to continuing conversations.
Very nice to meet you, Zach. Yeah.
And also, I dropped in some links to on the messenger group, and I'll add some more clarification and point out the article that's specific, that's relevant to what I was talking about.
Zach, would you be willing to present next week?
Yes, I actually have quite a different topic than what we were discussing on this matter. If that's okay, I don't know exactly what the format is looking like.
It's basically a 30-minute presentation and then question and answer. You're more than, we just want your brain, so you're more than welcome to present on a different topic if that's not too greedy of us.
Nope. I'm right there with you. I think that's where it's at. Is being able to take the best parts of what we got and share it with others and learn from each other. Yeah, totally.
Okay, well, we look forward to it then. And thanks again, Todd.
Awesome. Cheers, guys.
Thank you. Bye.
Bye-bye.